Welcome back to Unit 4. In Chapter 5, Section 2, we will learn about negative exponents and how to use proper scientific notation. We'll start with the basic idea of negative exponents. For any base x, if you have x raised to the exponent of the opposite of n, this is equivalent to 1 over x raised to the n. Let's look and see why this works. Suppose we have x to the 4th divided by x to the 7th. We know from the quotient rule that we could rewrite this as x raised to the exponent of 4 minus 7, and that simplifies to being x raised to the exponent of negative 3. Let's rewrite our original fraction a little differently. X to the 4th is 4 copies of x. X to the 7th is 7 factors of x. Simplifying, we find that 4 x's in the numerator will cancel out with 4 x's in the denominator. This leaves us with 1 in the numerator and x to the 3rd in the denominator. So now can you see it? X raised to the negative 3 is the same thing as 1 over x to the 3rd. Let's head over to example 1. In example 1, we simply need to rewrite this without negative exponents and then simplify. Here we have 2 raised to the exponent of negative 5. Using what we just learned about negative exponents, we can rewrite this as 1 over 2 to the 5th. 2 to the 5th is 32, so this becomes 1 over 32, and that's it. Let's look at example 2. In example 2, we're again going to rewrite the expression without negative exponents. We're also going to assume that all variables are non-zero so that we don't have to worry about dividing by 0. There's 2 pieces to this expression. We have an a raised to the exponent of 5 and b raised to the exponent of negative 4. A is already raised to a positive exponent, so what we need to fix is the b raised to the exponent of negative 4. We will rewrite that as 1 over b to the 4th. Now we have a to the 5th times 1 over b to the 4th, and we can simply write that as a to the 5th divided by b to the 4th. Let's keep going. In example 3, now we need to simplify x to the 12th divided by y to the negative 7th. Using what we know about negative exponents, the y to the negative 7th can be rewritten as 1 over y to the 7th. Well, dividing by the fraction of 1 over y to the 7th is equivalent to multiplying by its reciprocal, y to the 7th over 1. So now we have x to the 12th times y to the 7th. Or simply, x raised to the exponent of 12 times y raised to the exponent of 7. Do you see what happened here? By having a negative exponent in the denominator, we actually moved that piece to the numerator. When we have a negative exponent in the numerator, we can move that piece to the denominator and make it positive. When we have a negative exponent in the denominator, we can move that to the numerator and make it positive. Let's go on to example 4. In example 4, there's a few more things going on, but we'll take it one piece at a time. First, let's look at 5 to the negative 2. Since we have a negative exponent in the numerator, we want to move that to the denominator and make it a 5 squared. We also have an x to the negative 8 in the numerator. We will move that to the denominator and change the exponent to a positive. Next, let's look at our y to the negative 5th. It's in the denominator, so to make that exponent positive, we need to move it to the numerator. And finally, we have a z to the 4th in the denominator. Since that exponent is already positive, we won't move it. Cleaning this up just a little, we have y to the 5th in the numerator, 5 squared, or 25 in the denominator, x to the 8th in the denominator, and z to the 4th in the denominator. Let's go on to example 5. In example 5, we have b to the 7th times b to the negative 19. I'm going to show you 2 different ways to think about this expression. First, our product rule tells us that we can rewrite this as b raised to the exponent of 7 plus negative 19. That's really 7 minus 19, or negative 12. So we have b raised to the exponent of negative 12. To rewrite this without a negative exponent, we move it to the denominator. That's 1 over b to the 12th. Now let's think about it a different way. Let's switch this to positive exponents right at the beginning. So we have b to the 7th, and to change the negative 19 to a positive exponent, we can move it to the denominator. Now we have b to the 7th divided by b to the 19th. Now think about how 7 factors of b in the numerator can simplify with 7 factors of b in the denominator. This will leave us with no more factors of b, or 1, in the numerator, and 12 factors of b left over in the denominator. Either way you think about this expression, you still get the same answer. Let's go on to example 6. In example 6, we'll need to use a combination of a couple of rules. First, let's use our power rule. Our power rule tells us that we can rewrite this as x raised to the exponent of negative 6 times negative 7, the product of those two exponents. Negative 6 times negative 7 is positive 42. So we have x raised to the exponent of positive 42. Let's keep going. In example 7, now we have an exponent on the outside of these parentheses with a few different items inside. We will need to apply that negative 3 exponent to each item inside the parentheses. To the 3, the x to the negative 7, and the y to the 6th. So this becomes 3 raised to the exponent of negative 3 times x to the negative 7 raised to the exponent of negative 3 times y to the 6th raised to the exponent of negative 3. We can rewrite 3 raised to the exponent of negative 3 as 1 over 3 cubed. We can use the power rule to simplify x to the negative 7 to the negative 3 as x raised to the exponent of positive 21. We can rewrite this last piece as y raised to the exponent of 6 times negative 3, or negative 18. To rewrite this with only positive exponents, notice that the only thing left in the numerator is the x raised to the exponent of 21. We have a 3 cubed, or 27, in the denominator, and to make that exponent of negative 18 positive, we'll write a y to the exponent of positive 18 in the denominator. In example 8, let's look at one variable at a time. First, let's think about a. We have a to the 10th in the numerator and a to the 4th in the denominator. We could simplify this and write it as a to the 10 minus 4. Now let's look at b. We have a b to the 1st power in the numerator and a b to the 7th power in the denominator. So we can rewrite this as b raised to the exponent of 1 minus 7. And finally, we have a c raised to the exponent of 6 in the numerator and a c to the 7th in the denominator. We can rewrite that as c raised to the exponent of 6 minus 7. Simplifying, we have a to the 6th times b to the negative 6th times c to the negative 1. To write this without negative exponents, we need to move the b and c variables to the denominator. This gives us a to the 6th in the numerator and b to the 6th times c in the denominator. Let's go on to our last example like this. Here in example 9, we need to use our quotient rule and apply that exponent of negative 4 to both the numerator and the denominator. This will give us x to the 5th raised to the negative 4th in the numerator and y to the negative 4 raised to the negative 4 in the denominator. Using the power rule, we can rewrite this as x raised to the exponent of negative 20 in the numerator and y raised to the exponent of positive 16 in the denominator. To rewrite this with only positive exponents, our variable x needs to move to the denominator. So this becomes 1 over x to the 20th times y to the 16th. Now let's switch to talking about scientific notation. It may not seem like exponents and scientific notation go together, but they actually have a lot in common. Scientific notation uses exponents to write very large and very small numbers in a more concise way. To convert a number to scientific notation, rewrite it in the form of a times 10 to the exponent of b, where a is at least 1, but strictly less than 10, and b is an integer. Before we get started, let's quickly talk about our powers of 10 because they're a very important part of scientific notation. Starting in the center, we have 10 raised to the exponent of 0. We know that anything other than 0 raised to the exponent of 0 is 1. Moving to the left, 10 to the first is simply 10. 10 squared is 100. 10 to the third is 1,000. 10 to the fourth is 10,000, and so on. Now let's go to the right. Going down from 0, we would have 10 to the negative 1. That's 1 over 10, or 1/10. 10 to the negative 2 is 1 over 100, or 1/100th. 10 to the negative 3 is 1 over 1,000, or 1/1000th. And we can continue to the right in the same way. It really helps if you can see the relationship between the placement of the decimal point and the exponent of the 10. Starting with 10 to the 0 or 1, when we have 10 to the first power, we would move our decimal place to the right one place to get from 1 to 10. To get from 1 to 100 or 10 squared, we would have to move the decimal place to the right 2 places. To get from 1 to 1,000, we would have to move the decimal place to the right 3 places. That's equivalent to 10 to the third. So when we have a positive exponent of 10, that moves the decimal place to the right. Now let's look at our negative exponents. To get from 1 to 0.1, we would have to move the decimal place to the left 1 place. To get from 1 to 0.01, we would need to move the decimal 2 places. And to get from 1 to 0.001, we would need to move the decimal place to the left 3 places. Hopefully you can see the pattern, because this will make scientific notation a lot simpler. In example 10, we start with a very large number that we will convert to scientific notation, and then we have a very small number that we will convert to scientific notation. To write 320 billion in scientific notation, we need to write it as a times 10 to the b, where a is at least 1, but less than 10. That means our decimal place needs to be exactly right here between the 3 and the 2. In other words, our a is going to be 3.2. That's at least 1 and smaller than 10. Now, how many places do we need to move the decimal point to get from 320 billion to 3.2? 3, 6, 9, 10, 11 decimal places over. So in scientific notation, this is 3.2 times 10 to the 11th. Now let's look at our really small number of 0.000019. We again want to write this as a times 10 to some exponent b, and a needs to be at least 1 but smaller than 10. In order to do that, our decimal point needs to go right here between the 1 and the 9. That means our a is 1.9. That's at least 1 and smaller than 10. Now how many places to the right do we need to move our decimal point? 1, 2, 3, 4, 5. We needed to move it 5 places to the right. So in scientific notation, we will write this as 1.9 times 10 to the negative 5. Our really small numbers are going to have negative exponents for 10. Our really large numbers will have positive exponents for 10. Let's take a look at example 11. In example 11, we're going to do the opposite. We're going to switch from scientific notation back to standard notation. Looking at 4.06 times 10 to the negative 8, having that negative exponent means that we need to move the decimal place to the left 8 places. Doing that gives us the number 0.0000000 406. Notice that takes the decimal place from between the 4 and the 0, 1, 2, 3, 4, 5, 6, 7, 8 places to the left. So this is the very small number with 7 zeros before the 406. Now let's look at the second one. We have 2.88 times 10 to the positive 8. Since this time our exponent is positive 8, we're going to move our decimal to the right 8 places. This will give us the number 288,000,000. That moved the decimal place over 1, 2, 3, 4, 5, 6, 7, 8 places to the right. So in standard notation, this is 288 million. Going on to example 12, now we will multiply two numbers that are written in scientific notation. Notice that this is simply 4 factors multiplied together. 4.3 times 10 to the 16th times 1.6 times 10 to the negative 23. So let's reorder this a little bit. We'll start by multiplying together the 4.3 and the 1.6. This gives us 6.88. Next, let's multiply our 10 to the positive 16th and our 10 to the negative 23. Using our product rule, this is 10 raised to the exponent of 16 plus negative 23. And simplifying, we have 6.88 times 10 to the negative 7. In example 13, instead of multiplying two numbers given in scientific notation, we're going to divide. Think of this as 9.9 times 10 to the 5th divided by 3.3 times 10 to the negative 7. Hopefully that helps you see how we can simplify this. We can divide 9.9 by 3.3 and get 3.0. We can also divide 10 to the 5th over 10 to the negative 7th as 10 to the 5 minus negative 7. Simplifying, we have 3.0 times 10 to the positive 12th. Let's go on to our final example. In example 14, we're given that the speed of light is 1.86 times 10 to the 5th miles per second. How many seconds does it take light to travel this given distance? That's 13,950,000,000,000 miles. First, let's rewrite this giant number in scientific notation. We will write this as 1.395 times 10 raised to some exponent. How many places did we need to move the decimal to get from here all the way to here? That's 13 places, so this is 10 raised to the exponent of 13. So now we've written this large amount of miles in scientific notation. So how many seconds does it take light to go this distance? We'll take this number of miles and divide it by the speed, 1.86 times 10 to the 5th miles per second. And now let's divide like our previous example. We have 1.395 divided by 1.86. We can rewrite this as 1.395 divided by 1.86 times 10 to the 13th divided by 10 to the 5th. Well, that's going to simplify to be 10 raised to the exponent of 13 minus 5, or 10 raised to the exponent of 8. Looking at our units, dividing by miles per second is the same thing as multiplying by seconds per miles. This means our miles will cancel out, leaving us simply with seconds. Dividing 1.395 by 1.86, we get 0.75 times 10 to the 8th seconds. It's tempting to stop here, but remember, this value for a here needs to be at least 1, and 0.75 is smaller than 1. So we need to move this decimal place over to the right 1 place. But we can't simply just change this to 7.5. We need to adjust our exponent of 10. That will bring our exponent of 10 down 1 place. So now we have 7.5 times 10 to the 7th seconds. And that's how many seconds it takes light to travel that far. If you'd like to switch back to standard notation, we would simply move the decimal place to the right 7 places. This gives us 75 million seconds. And that will conclude this video lecture on negative exponents and scientific notation.